Well, welcome to ME760 Analysis 1. As you can tell, I'm not Dr. Abdu. He is away today. He threw a kidney stone last night, so he's in the hospital. And so he's asked me to come in and do this lecture for you. How many people have heard the story about the knights and the squires? Well, there's these three kingdoms, and they shared a border on a lake. And in the middle of the lake was an island, but no kingdom could agree to whom that island should belong. So they decided the only fair way to do it is, of course, to have a military contest. Whoever wins gets to keep the island. So one kingdom, the biggest of the three, it has 10 knights and 20 squires. Middle-sized kingdom, it has 5 knights and 10 squires. And the third kingdom, the smallest of them all, had 1 knight and 1 squire. So on the eve of the battle, the squires were all busy polishing the armor of their knights, sharpening their lances and getting the swords well used, cooking dinners because everybody had to eat before a battle, and except the smallest kingdom. The one poor squire had to do everything. And so he's got his big pot, he was cooking the meal and everything, and then he had to go and shine the armor and get the weapons ready. And he said, well, there are bears here, and I can't leave the pot down here. So he took a big rope with a noose on the end of it and hung the pot high on a tree. And they then finally had their supper, everything's done, they go to bed, and at dawn they wake. And the knights get together, kings get together one last time and said, you know, this is too important to risk the lives of our knights. Let's send the squires over to do battle. So the squires all went over to this island, and all day long a cloud of dust arose over the island, clanging of swords. Oh, battle went down, well, all day long. And just as the sun was setting, there was one squire left standing. And he was the squire from the smallest kingdom. Which just goes to show you that the squire with the high pot and noose is equal to the sum of the squires of the other two sides. Hey, it's a math class, guys. You've got to tell a math joke. Okay, I understand you've been looking at matrix multiplication, and we will look at that, some of the properties of this matrix multiplication. And so in some properties. One that's important is that in general, AB does not equal B times A, like ordinary number multiplication. In the mathematician's language, the matrices do not commute. And we can see a simple example of this, that if I take my matrices 9, 3, minus 2, and 0, and multiply it by matrix 1, minus 4, 2, and 5, what do you get for the upper left-hand corner? 15, right? The next one, should be minus 21, right? And I'll do the rest for you, 2 and 8. Obviously you know how to do this. Whereas if I take it the other way around, 1 minus 4, 2, 5, and 9, 3, negative 2, and 0, you end up with 17 and 3, negative 2, and 8. So, just a demonstration that the two matrices generally, you can't reverse the order of... Can you give me any matrices A and B that would commute? Yeah, anything with the identity matrix, right? So, I mean, there are some matrices that do commute, but in general, they do not. Now, what if I said that second property, if A times B equals 0. I double underline things to indicate matrices and single underline for vectors. Does Dr. Abdu do that, or? Okay. You know what an underline means if you're typesetting a book, right? When you have proof pages and you underline it, it says for the printer to put it in boldface. So in your textbooks, your vectors and matrices are in bold, right? Well, I can't do bold letters on a chalkboard, so I use the proofreader's marks. Now, what does that imply about A and B if the product of A times B equals 0? You would normally think, like if I had two ordinary numbers, A times B equals 0, then either little a or little b would be 0, right? It ain't so with matrices. It certainly is true. If one of the matrices was the null matrix, that certainly would happen. But I can have non-null matrices that go to 0. For example, let's do this example here. 1, 1, 2, 2 times negative 1, 1, 1, negative 1. And if you multiply that out, you get 0, 0, 0, 0. What is characteristic of those matrices, do you think? Is there anything special that you notice about one or the other matrix? What's the determinant of the first matrix? Or have you had determinants yet? 0. It's a singular matrix. Okay. And finally, the third property that you should notice, that if AC equals AD, and this does not imply C equals D. Just like this does not imply A or and or B equals 0. And just to give you a simple example of this, take 1, 1, 2, 2 times 2, 1, 2, 2. You just calculate that out, you get 4, 3, 8, 6, which is exactly equal to 1, 1, 2, 2 times 3, 0, 1, 3. And again, what's the gotcha here? One of those matrices, again, is a zero determinant. It's a singular matrix, right? Same as 1, 1, 2, 2, 1. And so in dealing with matrices, you can't treat it as if you would you're doing arithmetic. There are also some special matrices. One is you can have a diagonal, which is a square matrix with Aij equal to 0, I not equal to j. And in particular, we have the identity which we often give the special symbol I to, which is just 1, 1, 1, 0, 0, which has the property that, of course, A times I equals I times A, which is just equal to the A matrix. And we have also triangular matrices, which is a square matrix that looks like or we can have upper triangular. I assume we've talked about these before? Okay. So I'm just reviewing things. Another thing then would be transpose of a product of two matrices, in which we have that if I take the product of A and B and transpose it, that's the same as taking the product of B transpose times A transpose. Have you done this before in the class? So he's covered this?
Not that one.
Okay. How do you prove this? Well, most people try to do a 2-by-2 example, right? That doesn't work. A proof has to be in general, right, for an n-by-n matrix. So let's just calculate out the two sides and see what we get. Let's look at a proof here. So let's take AB transpose and call it the ikth element. Okay. And we simply expand that out. Well, we know how to do this, so that's going to be equal to the inside here, the curly bracket will be the summation, say, over J of Aij times Bjk, all transposed. And so this is some element Cik. Is everybody happy with subscript notation like that? And that's the formula you use for the product of two matrices. And so how do I take a transpose of this? What's the transpose of Cik? Cki. So this can be written as a summation over J of Akj Bji. Okay, explicit result. And so we now do B transpose A. I'm going to have the sum again over J of Bij transpose times Ajk transpose, which, switching the subscripts then, sum over J gives me ji times a kj. What about the two right-hand sides? They're the same, okay? Or, as mathematicians like to do it, QED. What does QED stand for? Yeah, quod erat demonstratum, or as students always say, oh, quite easily done. Now, why are matrices so gosh darn important? Well, because what is everything you do when you're trying to do computer work? Solve the Navier-Stokes equations, the heat transfer equations, whatever equation it is. What do you always have to do before you can solve it? Because calculus can't be done by computers. So you have to approximate them by linear algebraic equations, because all the computers can do is add, multiply, subtract, and divide. And so in all of your work that's going to involve any computation, you're going to be dealing with large sets of linear differential equations, ordinary linear algebraic equations. You can't have differential equations. You have to approximate those by difference equations, and leads to algebraic equations. So linear equations becomes an important topic, and we're going to look at it. It's important that you know something about it before you try to go to a computer and brute force things. So, use of matrices. Sets of linear algebraic equations. And such equations are like a plus 2x, or x plus 2y equals 5, 5x plus 7y equals 10. Typical example of linear algebraic equations. Or more generally, we can write them down as a11, and we'll call our variables x1 plus a12, x2 plus up to a1n, x to the n, equals some, say, b1. Then we have another equation, a21, x1, a22, x2, a2n, x to the n equals b2. And this continues on down. We get a n1, x1, a n n, x2, plus a n n, x to the n equals b sub n. And you guys trying fast and furiously to follow me and keep up, what do you realize by trying to use this representation for algebraic equations? You don't want to do it, do you? So, in a much more compact form, we can write this simply as an A matrix times a vector of the x values is equal to B. Now let me generalize this just for a second. This last equation, let's assume change this n to an m. So we have m. So in this case we have m equations in n unknowns. Now, for example, this might be a result of changing a source term in some experimental device, and you want to describe the response of the system by some sort of a linear combination of all the possible temperatures at, say, n points along a bar. And so you do experiments, and every time you do an experiment, you're going to get another equation for the x1 to xn. And often you'll come, you say, this is tedious, it's time to take a break and go to the lab and have a beer. And so you end up with not taking as many measurements as you should. And so if m is less than n, what are the solutions of such equations? X plus 2y equals 5. What can x and y be? You can come up with all sorts of combinations that satisfy that, right? And so we have what we call an underdetermined set. And you have an infinity of solutions. And this is clearly the problem that's encountered most. You wouldn't think so. But it's very often that, say you take the temperatures on the surface of a three-dimensional body, and you take thermocouples and you paste them on and you get 100 measurements. And you want to know what is the interior temperature. This is called an inverse problem. And you may set it up in a grid. Okay, so you have 10 by 10 by 10, so you have 1,000 points, but you have only 100 equations. This is clearly an underdetermined set of equations. You often encounter these sort of things. And this is a branch of mathematics that is onto itself, that there are clever ways. What you have to do, of course, is to get a solution like that. If you take the infinity of solutions and just start going through them, you'll find that most are silly. Half of them have negative temperatures at a node. Things like this, where you just can't have that, assuming you're working in absolute temperature scale, right? So you get meaningless results. So most of these infinity of solutions have no physical meaning. What's one of the things that you would expect in a three-dimensional cube in a temperature thing? They're all positive, right? And if I go from one node to another, you'd expect not major change. You'd expect the temperature profile to be basically smooth. You wouldn't expect to come up and go like that somewhere interior, unless I had two weird types of temperatures or some materials, but say it's a homogeneous mass. So there's a lot of stuff you have that's extra information that isn't contained in the equations. Like that it has to be positive, generally has to be smooth, can't have discontinuities. And so these are extra things that if you can find a way to add it to these equations, might give you a physical solution. And so this is called, using this additional information is called regularizing the inverse problem. You now not only want to find a solution of this, but satisfy these other constraints. And this is where a great area of research right now is doing how do you add these at different levels of constraints. And so this is an important problem. You won't encounter it before. People in math class, the mathematician says, forget it, it doesn't have a unique solution. Well, yeah, most of the problems we do are like this. And so you've got to find ways of regularizing the problem and adding extra constraints in it to give you a physical solution. So this is just a teaser to let you know what other things you can do with this sort of stuff. Of course, in school, what do they tell you that's always important to solve this thing? If m equals n, what do you have? You have, it turns out, a unique solution or no solution or an infinity of solutions. And we'll look at that here in just a second. And finally, if m is greater than n, you have an overdetermined which gives you no solution. Is that a problem? In fact, this is what you do most of the time when you're making measurements. Say you want to measure the conductivity of some material, and you assume, okay, it's going to be a constant plus maybe a certain temperature dependence. Okay? Like uranium oxide, very big for us nuclear guys in reactors because the thermal conductivity of uranium oxide changes with temperature. And so let's say we think it varies linearly. So we need to find out the conductivity is equal to alpha plus beta T. That's our model. Now, as good mechanical engineers, what do? Get up, put a source on this thing, put it in a microwave or something, and measure the temperature difference, right? And the heat flow. And I plot then conductivity versus temperature. And if I measure one point, what's my best fit for a straight line? Underdetermined, right? I can have an infinity of solutions. Get 2 points. Life is good when your major professor lets you just have 2 data points to fit a straight line through, right? But, nah, they're not like that. I say, take 15 more. Chunk, 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 chunk. Now, is there a unique solution? No. But what do? Because you got to have that correlation by tomorrow morning. Okay? Well, you do a least squares type fit, for example. Minimize the absolute deviation squared from the line. And so there are all these tricks for these overdetermined things. Mathematicians say, oh, no solution, forget about that case. Well, least squares analysis is a very important part of engineering analysis. So that's one of the things that you're going to encounter in linear equations like this sort of problem all the time. Okay, let's look at a simple example. Let's assume we have our x and y axis, and I can draw this better. Okay. And say these have intercepts 1, 1. And so this would be defined by our equations. X plus y is equal to 1. X plus y equals 0. And then we have an equation like this. We've got a line that comes through here, a line that comes through here. And so we'll have x plus y equals 1, x minus y equals 0. And finally we have so x plus y equals 1, 2x plus 2y equals 2. Heard that René Descartes, the famous French philosopher, went into a bar one day and the bartender says, "Hey, do you want a beer?" And René Descartes, very aristocratic, says, "Oh, I think not." And poof, he disappeared. Got to think about that one. What is one of his most famous sayings? Cognito Cogito ergo sum, I think, therefore I am. I think not. God, you're engineers. You're not artsmen, are you? Okay, so how many solutions do we have in the first case? So here we have no solution. What about this case? Clearly one solution. What about this case? And so we have an infinite number of solutions. Now, what's unique about the A matrix for each of these, that where you have no solutions or an infinity of solutions? 1, 1, 1, 1. What's the determinant? Have you covered determinants? You haven't done that yet, have you? A. Determinant of A, B, C, D is defined as AD minus CB, okay? Chunk, 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 chunk. Okay, we'll study later on, I'm sure, how to do it for an n by n matrix, but right now we're just doing 2 by 2 stuff. That's a definition. So in this case, you see the determinant 0. What's the determinant of this one? 1, 1, minus 1 times 1. So 2. Okay, what's the determinant of this case? 1 times 2 minus 2 times 1. 0, okay? So in this case is we have no solutions or an infinity of solutions if the determinant of the A matrix is equal to 0. So conversely, what is the requirement for there to be a unique solution? M must equal n, and the determinant must not vanish, right? Now, these equations we wrote here are inhomogeneous linear equations. Why inhomogeneous? You have terms involving that do not involve x1 or through xn, right? So that these are the inhomogeneous term. So a homogeneous set of algebraic equations is what? B is equal to 0, okay? So let's look at homogeneous equations. So in this case, B equals 0, and our equations are AX equals 0. So in general, we'll have, say, AX plus BY equals 0, and CX plus DY equals 0. And this, if we were to plot this, we'd have a line, in this case, that goes through the origin. So the slope of this line might be our minus A over B, and the slope of this line you can work out is minus C over D. And in good form, we should always label our axes, shouldn't we? So do you have a solution in this case? Yes, but it's what? The trivial, if we call it the trivial null solution, right? So but if I set that A over B equals C over D, okay, what happens to the two lines? They're collinear, right? And so, or we have this AD minus CB equals 0 equals the determinant of our A matrix is equal to 0. So in this case, we have this and so we have an infinity of solutions. So, how does this correspond to the inhomogeneous thing? This is two of the most important things that you need to remember for the rest of your life. If it's homogeneous and the determinant doesn't vanish, there's only the trivial null solution. Okay? If the determinant vanishes, you have an infinity of solutions. By corresponding, in the case of the inhomogeneous equations, if the determinant doesn't vanish, what do you get? A unique solution, right? Okay, that's non-trivial. Okay. And if the determinant vanishes, then you can have an infinity of solutions as well. So these are things that are subtly different between the homogeneous and inhomogeneous terms. And so how do you solve linear equations in general? 10 equations and 10 unknowns. Well, to any equation, you can add to any other equation, can't you? And replace the first equation by the sum. Or you can subtract, right? And you can multiply a row by a non-zero constant, right? And you do this to try to do what? Start out with, say, 4 equations, 4 unknowns. It's densely filled. Well, then you take the first equation, add and subtract the other 3 to get the first term to disappear, right? And then you take the next 2, so you get the second terms. Then you take the last one, combine it with one of the other 3. And so you get a triangular set of equations. And once you've got a triangular set of equations, is it obvious that it's easy to solve backwards? The very last equation is one equation, one unknown. Okay? The second one, 2 equations, 2 unknowns, but one of the unknowns now has been determined by the last equation. And you just go walk your way back up that diagonal and get all the other solutions. And this is the idea of Gauss elimination. And, but now, 10 by 10, if I gave you that for a homework problem, yeah, we could do it. But now, let's think about what we're going to ask the computers to do. So I have a three-dimensional, the one I know, three-dimensional neutron transport equation. It's a Boltzmann equation. It has 3 spatial variables, x, y, z. It has an energy. It has 2 directional variables, polar angle, azimuthal angle. And it will have time. So 3, 2 direction, 1 time. So you got 6, x, y, z, E, and R theta, you got 7 independent variables. Well, to take this equation, which is an interesting equation, a differential integral equation, and I approximate the integrals by discrete sum. We all know how to do that, right? If I have a derivative, you take it by finite differences, the difference of the value on either side of the cell, and divide it by the distance. And so you do, say you do 100 variables in the first direction, 100 in the y, 100 in the z, you have 100 values of e, you have 100 values for each of the two angles, and you break it up into, say, 100 time steps. So now you have phi of x sub y sub j, z sub k, e sub l, theta sub m, v sub n, time t sub o, or whatever it is. 7 independent variables in a grid. So how many different values of phi are you asking for in here? Well, you got 100 in each dimension, you have 7 dimensions, so I'm asking for 10 to the 14th unknowns. Now, so your matrix equation, A, is going to be 10 to the 14 by 10 to the 14. Now, I don't know about you, but that's something that I wouldn't even want to begin to attack, right? More importantly, how could you put that matrix into a computer memory? Hell, memory's cheap, they say, right? Not that sort of memory. And so, typically, the stuff you're going to be doing in engineering is going to involve not A is 2 by 2 and 4 by 4 and things like this that we do in the math class, but it's going to be these things with, you know, trillions, quadrillions of unknowns. Huge data set. And you can't even feed the data in, let alone store the x vector, which has 10 to the 14th numbers in it. Okay? So, but a matrix 10 to the 14 by 10 to the 14 is a big matrix. So, but yet, we do weather prediction, right? And that involves chopping up the atmosphere into grids, chopping up wind directions into speeds, trying to do the viscosity, solar insolation problem, cloud reflections, all of that stuff, and you end up with huge numbers of unknowns, with all defined by A matrix X vector equals B vector. Okay. Well, weather forecasting is one of the driving forces for building bigger and better supercomputers. I mean, there are a few problems. The big one was the first one was, of course, the development of the nuclear bomb when you had my problem of these huge numbers. And of course, you couldn't do it 100 by 100. You'd break the X up into maybe 5 points. And you have to reduce the scale so the computers of the day could handle it. But if you try to do, as you're going to learn about, have you talked about the inverse of a matrix yet? You will. Well, you know about it. You've heard about it before. You can't even calculate the inverse of that. I mean, the sun would die out before any computer could conceivably find the inverse of a 10 by 14 to the 10 to the 14th. And yet, weather forecasters solve it. It's going to be rainy today. How did they do it? You cheat, right? You say, well, I might be able to multiply that matrix by a vector. That's pretty fast these days. And what you do is you had 10 to the 14th, you wouldn't even do it. You reduce it to something, and the worst I've seen is like 10 to the 9th, 10 to the 8th unknowns. And those things, you can multiply a matrix into a vector. And what you do is you find another way of solving, instead of writing ax plus equals b, you write another x equals, say, mx plus g. So you have x, and you do this algebraically, and we'll show you how to do this next time. And then what you do is you guess initial value of x, so you end up with an equation that you will change for these large systems of equations. You'll take ax equals b and transform it into x equals, say, mx plus g vector. And what you do is you start off and say, guess a value for this, and then update it by this operation. So all you have is matrix multiplication. And you can show that if this converges, this equation is exactly the same as that equation. And so hence the necessity for developing these huge iteration schemes. And all the way through this course, even though it's supposed to be theoretical math, we're going to talk a little bit about some of the practical things that you will encounter when you try to solve these linear algebraic equations. But that's all we do, guys. You work with computers, you work with linear algebraic equations, albeit if you're doing Navier-Stokes or something, a large number of them. Okay, new appreciation for x plus y equals 2, 2x plus y equals 3. Yeah, there's a lot of interesting things. It's a really important topic in your analysis. Okay, I don't know what's going to happen to Dr. Abdu, but fun to come back and do a course I've always enjoyed. You sort of tell I enjoy this course, don't you? It's good fun. Any comments or questions before we leave? God, you guys are easy people to get over. She's heard this one, but yes, a question.
When you have an overdetermined set of equations, would you only have no solutions if they're not all linearly independent? Because you could have a solution if two were...
Yeah, if the number of extra ones were linearly dependent on the other ones, you can just throw them away, and you get a unique solution. But the usual thing is they're totally independent. They're measured data, so they're never exactly linearly dependent. And then you have to do some clever tricks with inverse problems. Yeah?
Did Dr. Abdu say anything about if we have questions on the homework that we do next week, if he's going to be around for email? I don't know if the hospital...
I don't know what's going to happen. Play it by ear, guys. You get a break as far as I'm concerned. Wasn't given any. He was in no condition. He was mumbling on the phone when I spoke to him in the emergency room. But okay, sodium ion goes into a bar. You've heard this. Sits down, orders a beer, and looks around and sees in the dark corner a chlorine ion. So he gets off his stool, walks over to the chlorine ion, starts beating the living the Jesus out of this poor guy. Then he gets tired and walks back to his bar. A few minutes later, a policeman comes rushing in up to him and says, "You're under arrest." He says, "Why? I'm just sitting here drinking a beer." "Oh, no. It's well known that whenever a sodium ion gets together with a chlorine ion, it's a salt." Okay. See you around, guys.